Today's lesson comes from Section 3-2, Solving Systems by Elimination. We will do our third method for solving a system. We already have graphing, substitution, and now elimination, also called linear combination in some textbooks. I like elimination only because it names the process, tells you what you're going to do. We're going to eliminate something to help us solve. So if you look at what we have, we're going to be using a system of equations in two variables. And an example looks like this. What if you have a system of linear combinations, system of equations in two variables, and you have the same coefficients somewhere, either x or y? You must eliminate one variable by adding or subtracting. So we found out in substitution that it was a heck of a lot easier to solve with just an x in the equation or just a y. You have one of each or two variables, then it makes it a little impossible. And so we're going to do some adding and subtracting to help us eliminate things using elimination. So if this was our system, x plus y equals 8 and 3x minus y equals 4, I would highly recommend in this situation to stack the two equations and then look at them. The x's have a 1 and a 3 for the coefficients. The y's have a 1 and a negative 1. To eliminate, easiest would be to get rid of the y's because 1 and negative 1 add up to 0. They would be eliminated if we added these two equations. So, doing that, we would get 4x equals 12. We would then divide by 4. 12 divided by 4 is 3. We get an x value of 3, then follow it up. Substitute that x equals 3 into one of the two equations. It's really your choice. I chose the top one because I believe it's easier. So it would read 3 plus y equals 8. Subtract 3 from both sides, y equals 5. Therefore, you have a solution of 3, 5, which means you should be able to tell me that these two lines intersect, and they intersect at the point 3, 5. Now, you're going to say, well, what if the coefficients aren't positive and negative values of each other? That's our next solution. We know we already have equations like that, so we'll move forward. What if they're different? So again, look at these two equations. 3x and 9x, nope, they cannot be added or subtracted. 2y and negative 8y, they cannot be subtracted. You now have some choice. And as I said here, if you look at it before we look at the work, I would multiply the top by 3, the top equation only, because that would get it to the 9 that we need in the bottom. And it would be nice and easy stacked. We could then subtract, which is what we did not do on the first one. We added. The y's do not have to be the same. That would be the variable that remains, and we'd be able to solve for it. So if we did this, multiply by 3 in the top equation, 9x plus 6y equals 66. That leaves our second equation unchanged. We could now say, to get rid of the x's, I will subtract. And in subtracting, remember you're subtracting everything. So 9x, take away 9x, 0. 6 minus a negative 8y is 14y. 66 minus a negative 4 is 70. Divide by 14 on both sides, y equals 5. And when y equals 5, you can use either equation. I chose the top one again, sometimes just because it's on the top. Put a 5 in for y. Be careful you're substituting it accurately. 2 times 5 will give us a 10 in the middle. Move the 10 over to the other side. Divide. We have a solution of 4, 5 for our xy ordered pairs. Again, this would show us, without graphing, that we have a system of equations that will intersect at the point 4, 5. 4, 5 is the solution of this system, again, without graphing. So it's quicker, shorter in most cases, saves time. Now, We can use addition or subtraction to get rid of them, but the key is you have to have like coefficients. If you have like coefficients to begin with, add or subtract right away. If you don't, you must get them to be like, and we use the idea of multiplying common multiples in this example. We could have used just as easily the 2 and the 8. If we wanted to multiply the top equation by 4 on this one, it would have also worked, but we then would have been getting rid of the y, and we would have solved for x. So the only difference there is we would have gotten x equals something first, rather than y equals. So you have some choices there based on what you see. Now, we can try a bigger system. Oh yeah, but I forgot one thing on this last one. What if you get down to the whole thing's worked out, and you get down and you have no variables remaining. So in this step right here, this would not have happened. Maybe you would have subtracted and you got no x's remaining, but you got a 3. And then you got equals 5. Does 3 equal 5? No, never. So if 3 does not equal 5, what is this saying? Well, we have a false statement. The only way we have a false statement is probably because the variables were eliminated due to one reason. They were eliminated because we have no solution. It's false, can't have a solution. And therefore, that would mean we have parallel lines. So false statement gives us the idea that we have a parallel system. Parallel systems will never intersect. You won't get an XY ordered pair, so that would be your solution would be no solution in this case, and you would know that it was parallel lines. Another scenario, what if, again, you did not get an X or a Y remaining? You just canceled your two equations, and maybe it says 0 equals 0. Everything wiped out. And it doesn't even have to be everything. What if you got 5 equals 5 as your final line? Okay, you could turn that quickly into 0 equals 0. But the statement here is, wow, 0 equals 0, 5 equals 5, those are true, and they're true every single time. And every single time would lead us to, there are many solutions to this, and many solutions would give us what type of system, and what would the graph look like. Those are the things you should be able to say if you see a solution like this. So we have many solutions, 0 equals 0, and we should be able to say this is a system where we have coinciding lines. So not all of them will be intersecting. Majority of them will, but you have to remember your other two scenarios, parallel and coinciding as well. Now for that, let's try something bigger. So we want to be able to use our strategy, which was let's get rid of one of the variables to get down to solving. Well, what if the equations have more variables in them than 2 to begin with? We want to use the same strategy, but obviously if we started with 2, we got it down to 1. That 1 helped us solve. We start with 3. We should be able to get it down to 2. From there, do exactly what we did, get it down to 1, and help us solve. So, in doing this, you want to look at all 3 equations stacked on top of each other and say, what would be the easiest variable to eliminate, to get rid of? And there's not always a good choice, but in this case, I would stay away from A. B, we could multiply by 12 to get rid of it. We got a 1, a 4, and a 3. A 5, a 3, and a 1 for the C's. We can also get rid of the C's. Your choice, but you can only deal with 2 equations at a time. So what I like to do on this one is to sort of number them so we know what we're doing. You can only work with 2 at a time. So if we work with 2 at a time and eliminate one of the variables, Then do the same thing with two different equations and eliminate the same variable. You must work on eliminating the same variable, otherwise you're going to have some confusion. So, if I start with equation 1 and 2, I could take, this would be my strategy, you don't have to write this down, but I'm going to take equation 1 as is, and I'm going to add it to equation 2 as long as I multiply equation 2 by 4. So I'm going to work on getting rid of the b's. So here's that set of equations. First equation does not change. Second equation, we said we wanted to multiply by 4, so that would be 8a minus 4b plus 12c equals 140. There's my two equations. You'll notice the b's are lined up. They are ready to go if I add to eliminate. So 3a and 8a is 11a. The b's are gone. 5c and 12c is 17c. And 22 and 140 is 162. I have a new equation that only has a and c in it, and I should be able to use it shortly. But now pick two equations, not equations 1 and 2, pick a different combination, and try to get rid of the b in those also. So if I do that, I'm going to take equation 2 and multiply it by 3 and add that to equation 3. Now there's other scenarios. I could have used equation 1 and 3, but I'd have to change everything. So I want to make it easier here. So equation 2 gets multiplied by 3 and would be 6a minus 3b plus 9c equals 105. Equation 3 does not get changed. So I'm just copying it. Now I look at what I have, and again I'm saying b's are what I want to eliminate. B was exactly what I eliminated the first time around on this, and I would do so by adding. So here we go. 6 and 7 is 13a. 9c and negative 1c is 8c. And 105 and 26 is 131. Now look carefully, you have two new equations, both in terms of a and c, that you could now use together. And I'm going to leave it at there for now, and we can come back tomorrow and talk. I need you to finish and see what kind of solution you get. We are down to the point that you have two variables and two unknowns. So that will take on the same situation we already demonstrated, get it down to one variable. And as soon as you have that one variable you can solve, you would have either A or C, depending on what you choose. Once you have A or C, you can get the other one that's missing, A or C, by using either one of these equations to substitute. Once you have A and C, you could substitute A and C into any one of the three originals to get your B. So you should end up with an A, B, C, an ordered triple when you finish. So good luck. We'll talk about that tomorrow along with those other things, pros and cons. We should be good to go. So bring any questions, any confusion, and the rest of these problems to class